goes with, just so you can orient yourself a little bit. This is the end of the first section of Unit 2, where we're solving quadratic equations. We've practiced simplifying radicals, okay? So, no square roots on the bottom, simplifying a square root so we can couples go out, singles stay in stuff. Here's a problem that summarizes everything we did in section 1. We can do this problem, we can do it all, right? There's plus one other one we'll do in a little bit. Those two combined cover all those concepts. So let's look at this. How do we solve a problem like this? How do we solve this quadratic equation? What's our strategy? And then let's get an answer. Okay, subtract 10, and how come? What's our overall strategy here? Okay, isolate x, right? We got a single x we can point to, so we're going to isolate it. So we just reverse order of operations. And so outside of parentheses, we add subtract. Good, so we subtract 10 from both sides. I will put this up, this stuff will be up on the Moodle site today, but I think it's maybe not a bad idea to just kind of work through this with me in your notes. All Chromebooks should be completely closed though. I don't want to see anything open. There we go, thank you. Okay, so we cancel the 10s. We get 4 times the quantity negative 4x minus 5 squared equals 288. Okay, so now one other issue. We've talked about this a bunch, but I really want to hammer this home. Can we distribute the 4? No, we cannot. And how come? What's the red flag here that tells us right away we can't distribute the 4? The square. Good. Okay, so because of that, because of the exponent, we can't distribute the 4, right? Not an option. So what do we do instead? What's our next step? Divide. Good. Good. So we divide each side by 4 to undo multiplying outside of parentheses by the 4. Good. And that gives us, then we've got the quantity negative 4x minus 5 squared equals 72. Okay? Now what? Square root. Square root. Do we want to square this out? No. Could you? Yeah, you could, but you make the problem way, way harder, right? If we were to FOIL this out and get x squareds and x's and all that stuff, this becomes a next level harder quadratic equation. And why do that, right? Why do that when it's the easy kind? It's the kind where you can isolate x, because those are the easiest, right? So we square root both sides. Thanks. So we square root both sides. What's that do to the left? Get rid of the squared. That's our goal, right? We're trying to isolate the x. We want to just peel everything away from the left side except the x. We want to eventually leave the x by itself. So we cancel the squared. That's good. So then we get negative 4x minus 5. Do I need the parentheses anymore? No, they're extraneous, right? They don't do anything for us. We needed them here because we were squaring the whole thing, right? But now that we've undone the exponent, there's no reason to have those parentheses anymore. Is it incorrect to put them there? No, not really, but in math we want to write things as simply as we can. Okay, so we wouldn't include them. What must I include? This is the easiest thing to forget. Plus or minus, good, because I square rooted both sides, so I gotta have my plus or minus. And now I've got to simplify the square root of 72, right? Okay, so let's focus on that. We got our 72. We can slice and dice this a bunch of ways, but what's probably the best way to break up the 72?
9 and 8.
I'd say not 9 and 8. It's going to work, but there's a better one. 36 and 2. How come? Because 36 is a perfect square. There you go. So we're going to get 36. 9 is, you're right. 9 will work. But the problem with 9, and we'll look at it the other way too, because I want to really reinforce this. The 36, we want to get the biggest perfect square we can, because now if I pick 36, we know that that's breaking up into 6 and 6. I got a couple of 6s in one step, right? And then I've got a single 2. If I were to do this the other way, so if I were to do 72 and break it up into 9 and 8, yeah, it's going to work. 9's going to break up into 3 and 3. 8's going to break up into, what, 2 and 4? But then I've got to break the 4 up into a 2 and 2 also, right? And what do we end up with? A couple of 3's and a couple of 2's. What's 3 times 2? 6, right? So we'd rather bail off that factoring train early if we can. We'd rather just find the biggest perfect square factor we can, so we don't have to go through all this extra factoring, right? Does that make sense? Okay? So we end up with 6 radical 2 is our simplified version of square root of 72, right? And now, what? Last 2 steps. Add 5. Okay, good. So where do we put the 5? Front of the plus or minus. So those cancel. Negative 4x equals 5 plus or minus 6 radical 2, and then last step. Okay, divide by the negative. Now talk to me about that. Do I want to divide, get a common denominator in this case, or not?
No.
I do not. How come? Because it's plus or minus, and these terms don't combine, right? Now, if this was 5 plus or minus 6, then yeah, you could, if you wanted to, just put the negative 4 on the bottom and get the solutions, simplify when it's a plus, get an answer. Simplify when it's a minus, get an answer. That works okay because in that case, the numbers combine as integers, and so we know we're going to get a real simple answer. But when these two numbers are incompatible, when they don't combine easily, then we want to divide separately, right? That makes sense? Because then we can simplify each fraction by itself. Everybody get that? Okay, so our rule of thumb is split this up, and what about this guy? Do I need to divide the plus or minus term by a negative?
No. Just not making sense.
It doesn't make sense because we've already got both signs accounted for, so why make it extra hard, right? We'll just divide by the absolute value, which is positive 4, because we're getting both signs anyway, right? And so we end up with then our final answer, x equals 5 over negative 4 is negative 5/4. Let's put the negative out front, right? We never want to have it on the bottom, though. That doesn't make sense. You can put it on top or out front. I think it's better just to put it out front because the 5/4 is just a number, right? It's a fraction, but it's a number, and this is telling it's a negative number, okay? Plus or minus, what can we do with this? Okay, the 6 and the 4 are going to reduce, aren't they? Right? So that's going to reduce to 3 over 2, so we end up with 3 radical 2 over 2. So in Moodle, you got to enter those separately as 2 different answers. One with the plus sign, comma, one with the minus sign. Right? Okay, no big deal though, right? The only additional wrinkle here that makes this any harder is just that we ended up having, when we simplified the square root, it didn't all go away. Right? We ended up with some stuff stuck in the square root. Questions on that one? Okay. All right, so then we went through some pretty simple stuff that just involves imaginary numbers, complex numbers, right? And this assignment should be a really quick one. All it's really about is just understanding what a complex number is, what standard form of a complex number is, and how we can graph them in the complex plane, right? But you're not really doing any algebra here. This is just kind of getting familiar with this number system, or with this number set. So what is standard form for a complex number? How do we? A plus BI, good. So what's the real part then? A, good. What's the imaginary part? B, good. So all they're asking you to do is just, understand that. This is pretty quick. What's the real part of this one? They want you to enter the real part and the imaginary part separated by a comma. So -8, comma, what's the imaginary part? That's it. Okay, no big deal. How about something like this guy. So identify the graph of the complex number 8 minus 6i. So what's the real part? 8. What's the imaginary part? So then in the complex plane, remember we graphed the real part on the real axis, the horizontal axis, and we graphed the imaginary part on the vertical axis, the imaginary axis. And the representation of this number then would just be a vector starting at the origin and ending at the point with those coordinates. So which one is it? Which one was it? Where? Oh, right here. There you go. Yeah. Over 8, down 6. Perfect. So over 8, down 6, that's it, right?
How come the, oh, wait, never mind.
So that's our point. FC answer.
How come they're rates?
Say it again.
How come they're rates instead of, they have arrows on them? Like they can see long.
Okay, so right. So they're not rays. Those are vectors. Right. So vector, we haven't talked about vectors. We really won't talk about vectors this year except this one time. That's something you will next year. Next year you deal with it in pre-calculus. At the end of the year I might do just a little short piece on vectors at the end of the year. All that represents, a vector is, it looks like a ray, it looks like an arrow, but it's not. It doesn't go forever. It starts here and it ends here. The important thing about this is where it ends, right? So you wouldn't even have to write this as a vector. You could even just write it as a point in the complex plane, which would just be that point right there. Okay? The reason we include, I think the reason that it's important for you guys to see this as a vector is because it's important to think about the magnitude of the complex number, the modulus, as being the length of the vector. Okay? But that's really the only reason we would even bring that up this year. Okay? That make sense? Questions on this? Okay? Good, good. All right, so speaking of that, oh, almost. Write this as a complex number then. What's it going to look like? Okay, so z equals a plus bi. Well, what's a in this case? Negative 8 is the real part. What's the imaginary part?
0.
So that would be written in standard form if we included the 0 times I, right? We really need to include the 0 times I, though?
No.
What's 0 times I?
0.
0. So the answer is just negative 8. Okay? Make sense? Okay? So here's where the vector part becomes a little more important. If we're trying to write the modulus of z, so they're giving us some complex number. What is z written in standard form? But just what is just the complex number though, first of all? Negative 6.
Minus 9.
All right, good. Okay. So A is negative 6, B is negative 9, right? Just the coefficient, just negative 9. And if I want to find the modulus, remember the modulus, or the magnitude, same thing, of the complex number is always the square root of what? Good. A squared plus B squared. So we're just going to get the square root of negative 6 squared plus negative 9 squared. What is that? 36 plus 81. So square root of 117. 117. And that's, we can't simplify that, can we? Or actually, maybe we could. I think we could. Yeah, so if I write that in simplified form, 117, what's going to go into 117? 3 would. Okay. And then what's left then? 3 goes into that. 3, and that gives me 2. So 39, right? Now what? 3 and 13. So what do we end up with?
3 radical 13.
So this becomes, okay, 3 radical 13. Okay, make sense? Questions? Okay, no big deal. So So that's what that whole assignment is about, is just, getting used to representing complex numbers in the complex plane. Okay, next. So then, next assignment, practice 2 in section 2 is about arithmetic. So this one was adding, subtracting, and multiplying complex numbers. Adding complex numbers, super easy. All you're doing is combining like terms, right? Subtracting complex numbers, remember, it's almost the same thing. You're just going to distribute the negative sign and add like terms. So you add the real parts and the imaginary parts separately. Let's look at one like this. Here's the hardest problem that you got in that whole section, was taking a product of 3 complex numbers. Not a big deal, but you got to remember something about when you multiply numbers, right? You multiply numbers in pairs. You can't do this all at once. So what's our strategy here? So we got to multiply 2 of them, right, and get a simplified answer for that product, and then whatever we get, we multiply by the third. So for example, we'll just ignore this one initially and just multiply out the product of those 2 complex numbers first, right? So let's just remind ourselves how we do that. If we're going to multiply these together, what do I do? What am I doing?
The rainbow thing.
The rainbow thing. So I'm foiling, distributing, whatever you want to call it. If I distribute the 6, I get
Point 1. Negative 24i.
okay, if I distribute then the 2i, minus 8i squared. Okay, but what is I squared always equal to?
Negative 1.
Okay, so what's our rule then? When we end up with an I squared term, what do we do to that term?
Positive coefficient.
Okay, so we just flip the sign of the coefficient, right? We just change the sign of the term. So this one, instead of writing minus 8i squared, we automatically write it as plus 8, right? Then all we have to do is add like terms. So what do we get? 24 plus 8 is 32. Negative 24i plus 8i, 16. Heard it? So then that's the result. When we multiply those first 2 together, we just get that, right? Now what do? Well, I bring down the third complex number and I start over, right? So this one you have to do in increments, okay? But you got that. I'm not going to finish it. You guys can finish it. Okay, well this got a little harder though, dividing complex numbers. So the next assignment's about dividing complex numbers and doing some harder, simplifying some bigger, harder expressions involving complex numbers. So let's focus on a couple of these. What's our strategy for simplifying a quotient of complex numbers? Good. So we can't have i's on the bottom, right? We got to get rid of the i's on the bottom. And our strategy was multiply top and bottom by the complex conjugate of the bottom, right? So we're going to multiply top and bottom by the same expression as the bottom, but we're going to change the sign between the real and the imaginary parts, right? So radical 7 minus radical 6 times I. Make sure the I gets outside of the radical room, right? Okay, so I want to help you save a little work on this, though. There's something we can, because I've been kind of looking at what people have been doing on this, and people are doing this right, but you can do it more easily in some cases. Whenever I multiply complex conjugates together, remember what happens. Let's not be specific. In math, we want to be as general as we can. We'd rather come up with a general rule that we can apply in all cases, right? So let's not even pin ourselves down to the square root of 7 for the real part and the square root of 6 for the imaginary part. Let's just call it a plus bi. If I multiply a plus bi times its complex conjugate, which would be what? A minus bi. What happens? If I distribute the a, if I distribute the a, I get my a squared minus abi. If I distribute the bi, I get plus abi minus b squared I squared. So a couple important things happen there. What happens to the cross terms? They always cancel, right? Every time they're going to cancel. So I end up with an a squared. Now what's minus b squared times I squared? Plus b squared, yeah, right? Because that's all that does is change the sign of that term. So we always get a squared plus b squared every time, right? You don't have to go through the process every time. You know on the bottom, that's going to happen. So that allows me to go a little quicker on the bottom. So what's a on the bottom? Square root of 7, okay. What's b? Square root of 6, right? So what's a squared plus b squared? 7. Because it undoes the radical, right? What's the square root of 6 squared? 6. Right? Bottom's easy. Top's going to take a little longer, right? On the top, we do have to go through the whole distribution process. So I distribute the 1. That's easy. Just gives me that, right? So I get 1 plus, square root of 7. Square root of 7 minus the square root of 6i. If I distribute the 3i, what's that going to give me? What's 3i times the square root of 7? The I is just, I know I'm going to get something I, right? What's 3 times the square root of 7? Exactly that, 3 times the square root of 7. Right? Okay, 3i times negative radical 6i. So I know I'm going to end up with an I squared at the end of that, right? What is 3 times negative the square root of 6? Negative 3 radical 6, okay. And we've got our I squared there. So what's that term going to become? Yeah, plus 3 root 6, right? Just change the sign and the I squared goes away. And so this looks, this kind of is messy. On the bottom, you've got your 13. Now what? So let's combine the real parts on the top. So the terms with no i's in them. So I'm going to get a square root of 7 plus 3 radical 6, right? So there's the real part. Now what about the imaginary part? So the imaginary part, we've got this term combined with that term. Now, what I always do in these situations, and this is up to you, I would always put the positive one first. So you end up with, I get plus something minus something, instead of have to do plus a negative plus a positive. See what I'm saying? Doesn't make any difference, but I always would tend to do that. So let's put this guy first, 3 radical 7 times I minus square root of 6 times I. Okay, now how do we deal with this mess? So these two terms right here, what can I do with those two? They both have an I in them, right? Okay, so how could it looks messy, but couldn't I just factor out an I? I could make that whole thing. Wouldn't it be easier to write that as 3 radical 7 minus the square root of 6 times I? Everybody see that? This looks terrible, but it's just a number, right? It's just some number times I. And that's all a complex number boils down to, is a real part plus an imaginary part, which is just some number times I, right? So then we can split this thing up. We've got this plus sign in the middle that really separates the real part from the imaginary part of that complex number. So let's break this up into separate fractions then. On the real part, I've got a common denominator of 13. So I've got the square root of 7 plus 3 radical 6 over 13. There's the real part, no i's involved, right? plus the imaginary part. Well, I've still got my 13 on the bottom, but my imaginary part looks like 3 radical 7 minus radical 6, and then I'll just pull that I outside of the whole thing. That looks more like it's supposed to now, doesn't it? Our goal, if you look at the instructions up here, the goal says you want to write it in standard form of a complex number. So some real number with no i's, a, plus some real number b, which is multiplied by I. Those don't have to be pretty numbers. They could be really ugly numbers, but they're still just numbers.
This all we can see.
And that whole thing, yeah, that's my answer, isn't it? So the last thing we'd want to check on this is, okay, now on the real part, could I simplify this? So I probably want to break this up into separate fractions, right? In this case, I don't need to because none of them simplify, but what if that was like a 12 on the bottom? If that was a 12 on the bottom, the square root of 7 over 12 doesn't reduce, but 3 radical 6 over 12 would reduce. Everybody see that?
Yeah.
So we'd want to write that then, we for sure would want to write that as the square root of 7 over 13 plus, that would reduce to the square root of 6 over 3, right? Okay. In this case, we can't do anything with it, so splitting it up doesn't really accomplish anything, but it doesn't hurt anything either, right? So it might be a good idea in those situations just to always break it up into separate fractions. So there's my real part. What about over here? Plus, I can't do anything in this case either, but let's go ahead and break this up into separate fractions just in case one of them reduces. Minus radical 6 over 13. And this time I do need to put that whole thing in parentheses because it's all times I. Okay. Do I need parentheses around this? No. Could you put, I mean, would they potentially serve a little bit of a purpose? Maybe, because it's all the real part, isn't it? So you're not penalized for putting parentheses around that. It makes, I mean, I can see why a person would, right? But you don't technically need to.
Whoa, that's interesting.
Okay. Does that make sense? Yeah. Did I? Yeah, a little, another one, all right. You guys are really good at that, I gotta tell you. I would never catch me doing that so often. Okay, so does that make sense? You need, if you haven't done this one, obviously you need to get some practice to get this down. But do you understand the structure of that problem? No? Ask a question. Which part? Ties being brick. Okay, so let's go back. We did the problem. Let's just go back and look at kind of what we did. Let's summarize what it is we did with this thing. Thanks. All right, so to summarize, what did we end up doing here? Anytime that we have a quotient, so we're dividing complex numbers, the way we simplify that is we're always going to multiply the top and bottom by the complex conjugate at the bottom, right? That can get messy when we do that. On the bottom, when we multiplied the square root of 7 plus the square root of 6 times I times its complex conjugate, we just got 7 plus 6, right? Because it's always going to give us a squared plus b squared. So that part works out great. It's always going to. It's always going to be easy. The part that could be really messy, and I picked the hardest possible one to do here. I mean, this is really bad because it's got radicals within radicals. But on the top, when we boiled all this out, we ended up with 2 real terms and 2 imaginary terms, right? Just like you do when you multiply any 2 complex numbers together. And so we wanted to turn that into, collect the real ones together and collect the imaginary ones together, and just split this apart into ultimately a real part with no i's, and then the part that had i's, that needs to be represented as just some number times I. Let's do maybe one more of these. I kind of want to get a feel for this. How much time we got? 3 minutes? That's it? Okay, rather than move on, give me a 1 to 5 on this. 5 meaning, I think I got this down completely. I wouldn't expect to maybe see a ton of those. 1 meaning no clue, or somewhere in the middle. Okay.
Oh, yeah, I can't do that.
Definitely.
All right, all right, all right.
I got it. Oh, man.
Yep, you betcha. Yep.
How I do that?
Okay.
It keeps coming up with like square root numbers, and I don't.
Yeah, yeah. Well, that's just square root of a squared plus b squared. Square root of 6 squared plus negative 9 squared. That's it.
Oh, so that's all I'm doing?
Yep, that's it.
Okay. So that would be 36.